Okay, this lecture actually is come about because I was trying to help my student with answering a tutorial from a university financial maths course. So in this tutorial, I will explain a few things. First is the Black-Scholes model for pricing a call option. I will explain what is a call option first, and then I'll explain what is the pricing, how to price a call option, and then I will try to prove this part of the formula, and I will also try to prove that the I will try to prove that this is equals to this. I also try to find d the c naught over ds naught. We'll understand what are all these later, but okay, let's say if you happen to be to do the same assignment, okay, you happen to do the same type of assignment that you are asked to show all these, then this tutorial will be helpful to you. So one of the last thing is I will show that this is equals to this, and sigma stand for volatility. Okay, so I will explain all these symbols and what they mean. Okay, so the first thing that we're trying to achieve. Okay, so the techniques used here mainly will be calculus. Okay, so let's first explain what is an option. Now in life, if you are given an option, that means you can choose whether to do something or not to do something, right? Or to be presented a few choices, you can take up one of them. Option means the same thing. Okay, but option in finance usually is implied there are two types of option. One is a call option and one is a put option. So a call option is an option to buy, and a buy at a certain price, agreed upon price, and a put option is an option to sell something at an agreed upon price. So to give an example first, so let's say today a share is priced at $3 in the market. Okay, a share is priced at $3 in the market, and Bob, a person, wants to buy the share 2 months later. He doesn't want to buy now. Okay, the characteristic of option is the option is pertaining in the finance is usually in the future. That means the right to buy a share at a certain price in the future. Okay, so it's not today, but he does not know what the share price should be after 2 months, right? Why do we need an option to buy? Because at a certain price in the future, because we do not know what the share price would be. If we want to buy the share today, we know what the price is offered in the market. We should just buy it. There's no need to have an option in a sense. But because we want to buy it 2 months later, and we want to have the option to buy it at a certain price, okay, that we use a call option. So he wants to have the option to buy the share at $2 3 months later. So $2 will be the price that he wants to buy, and someone must agree to sell to give him that option before that option would exit. So Opus decide that he will give Bob that option. So you give Bob the option to buy the share 2 months later at $2. So $2 is what we call the strike price or the exercise price. That means in this call option is a kind of the contract between the two person. Is the Opus will agree to sell Bob. If Bob decides 2 months later to use that option to buy from Opus the share at $2, then Opus is obliged to honor the option and to sell Bob the share at $2 so that Bob can purchase it at $2. Then we call $2 the strike price. Okay, then 2 months, because it is 2 months from now, then we call it the time to maturity, which is the T in this symbol. In this formula, T is the time to maturity, K is the strike price. C naught, this is the price of the call option. Okay, why do we need a price for the call option? Because nobody is going to give you an option for free, because it has by giving you the option, the Opus is taking some kind of risk. What if the share is priced at $50 in the market 2 months later, and he gave you the option to buy at $2 means he is losing out or giving up the opportunity of earning $48 more. And then why would he give you that option if not because you are paying him something to give you that option? So Opus will be willing to sell you that option if you are paying him something. So let's say if Bob pays him $150 to have that option, no, $1.50 to have that option, then C0 is the price of the call option. So this is how it works. Then after 2 months later, okay, there are 3 possible scenarios because sigma is what we call the volatility of the share price. That means how the share price is likely to fluctuate. So it's a measure of how volatile or how wildly share price fluctuates. So because the share price is volatile or because the share price changes, 3 possible scenarios can happen at 2 months time. One is that the share price is falling below the $2, the price they agree to sell or buy, right? Or it could be more than $2, or it could be exactly the same at $2. So let's see in these 3 scenario, what would Bob do? Okay, if the share is sold at $1 in the market, that means buyers and sellers are transacting buying and selling the share at $1 in the market. Bob, as the person who wants to buy, as a buyer, will buy the share at $1 instead of exercising the option to buy at $2. So although he bought the call option, the money was already paid to Opus when he bought that option. So he wouldn't get it back. Even if he decide not to exercise the option, he would not get the $1.50 back. That is a sunk cost. Means he already given to Bob to have that option. Now, the option left with Bob is whether to exercise the option. That means whether to buy the share at $2 from Opus or to buy the share at $1 in the market. Of course, now Bob can buy it cheaper at $1 in the market. He wouldn't exercise the option to buy at $2 in the market. So therefore, he will just give up on the option. The $150 was already paid to Opus when he bought the option, so he couldn't get it back, right? So he will not exercise. He will just buy it from the market and get at $1. Okay, so in this case, it said that the loss made by Bob overall is $1.50, right? And let's say in this scenario 2, let's say the share is sold at $3 in the market. Now the share is sold at a higher price in the market than if he bought with that option. So now Bob will exercise the option to buy the share at $2 from Opus. Okay, after he buy the share at $2 from Opus, he could sell in the market for $3. It means he potentially earned $1 for nothing, but he's still making a loss because although he earned $1 here, he lose $1.50 while he pays $1.50 upfront. So overall, there's net loss of 50 cents. All right, in order to break even, that means to make the price of the option worth it, the share price has to be at least at the 2 months time should be at least $3.50, right? If it's $3.50 and he is able to buy using the option at $2, then he gained $1.50, which is just enough to pay back on the price of the option. All right, okay, so then the next thing is no, the option is not the share. So that means if you have the option, doesn't mean that you use only an option whether to buy. It doesn't mean that you have the share. It's a different thing. The option and the share are separate. The option price and share price is separate. They are not the same thing. This is something to note. So in the case where the share sold in scenario 3, when the share is sold in market at $2, then it does not matter whether Bob exercised the option or not, because anyway, whether buying from market or buying from Opus is still $2. Therefore, he will not exercise the share or exercise the option. He will not exercise the option, or he would exercise the option, but there's no point. So because he could buy from the market anyway, so then there is he lost $1.50 from being bought the option. Okay, so that's it. So this explains what is an option. Now I'm going to do this video in 4 parts. Okay, so this is part 1 of the video. So I'm about to stop this video here, but I'll just explain one more thing here. So this formula is because I've explained what is the option, and I explained that an option is given only after you pay a certain price. And what is the price, what is the right price for such an option? Like people have been thinking about it, and some mathematician has come up with such a formula for that is reasonable for pricing an option, and it factors into things like what is the current price of the share, and what is the strike price that the two guys agreed upon to buy or sell. R is the interest rate, let's say, because the money, if you don't buy the option, you could keep in the bank to earn interest, and so we need to factor into what is the interest rate, and that will decide what is the share price of the call option. And T is the time to maturity. That means from now to then, what to the time that you can exercise the option, how long is that, right? And then the D1 D2 D1 and D2 here, the D1 and D2 here actually is an elaborate formula. Okay, so this is the log function over here. S naught again is the current price of the share. R and T I've explained, K also I've explained. So only the sigma, this sigma means the volatility of the share. That means how share price, so how much the share price fluctuates also affect the call option price. So N is the N here, actually the whole thing here is a function. D is the inputs to the function. D1 and D2 is the input to the function, and this function is what we call the cumulative distribution function for a normal distribution. If you learn statistics, then you know what is a normal distribution. Normal distribution follows a shape of the bell curve. Alright, so but we shall not do into it deeply here, so we just study some statistics to find out about what is the normal distribution. It will give you a better idea, and also of course you need some concepts of what is a function. Okay, function is a, let's say, a number input into this then we will calculate using the rule, the formula for the cumulative distribution function, and we will get a value which we will use to calculate the call option price. Okay, so I will pause the video here, and then I begin part 2 in another video. Okay, all these videos can be found in my site www.our.com. This is where I organize all my videos, and you will be able to find it there, right? Okay, thank you. So I'll pause it here. Okay, this is the second part of a 4-part video addressing a tutorial from financial maths. It's about the call option, Black-Scholes call option pricing model. But part of it, of the tutorial, we are asked to prove that this is equals to this. As I mentioned in the previous tutorial, part 1, this is the strike price, this is the interest rate, this is the time to maturity, this is the probability distribution function of the, and then this is the probability distribution function also, and this is the current price of the share. So this notice different from the there's a difference from, although this looks like very similar to the thing here. Okay, it's very similar to the thing here, and this thing here looks very similar to this thing here, but they are not the same. There's one major difference, is that there is no, you see this thing here, this prime, and this what you call the prime here. It means that there's no prime over at here. That means this means that this is after this normal, this is cumulative cumulative distribution function has been differentiated, and to arrive at the probability distribution function. So m prime x we call the normal PDF, or the normal distribution probability distribution function, but this is the cumulative distribution function CDF, so there's a difference. If you want to know more, you can Google cumulative distribution function and probability distribution function of a normal distribution function. Normal here doesn't mean the normal, it's a specific type of not distribution, probability distribution. So now I'm going to prove this. So I'm going to prove from the right hand side to the left hand side. That means here I'm going to prove from here to arrive at here to show that they are equal and answer the question from the tutorial. So first thing, okay, okay, let me get some power source. So the first thing that I'm going to do is ke minus r, that means the right hand side of here. I'm going to change it. Let me get some power first. Okay. I hope it works. No, there's not enough power. Okay. Okay, and it's getting. Yep, should be getting enough power now. Okay, so then we will, okay, so for this part, ke minus rt m prime d2, okay, I'm going to show this. So using number 3, so I'm using 3, so this is the call option pricing formula. So the d2 comes from here, d2. Okay, so this d2, using this formula given, this definition of d2, I change it to d1 minus sigma root t. I change this d2 to d1 minus sigma root t. Alright, I've changed nothing else except that from coming from here to here. So, and then using number 4, this number 4, okay, this is the probability distribution function formula. So you can Google for it, you'll find that this is the normal probability distribution function formula. So that means when I change my x, right, if in the function, if I replace this x by 3, this x has to be replaced by 3. If I change this to 4, then this x has to replace by 4. That is essentially what it means by a function. So then in this case, because my x has been changed to d1 minus sigma root t, so therefore the x here has to be changed to d1 minus sigma root t, and we square it, and everything else would be the same. Root 2 pi, this one is root 2 pi, e we have it here, 2 we have it here, so minus we have it here. So it's exactly the same except that the x has been replaced by d1 minus sigma root t, and there we have this ke minus rt, where I'm not changing anything. So now using 5, number 5, which is this, the quadratic expansion formula for the top part, okay, because this is the bracket square, same thing like this. Now my a is my d1 and my b is my sigma root t. So when I do this expansion, d1 square is my a square minus 2 times a is my 2 times d1 and sigma root t. So you just match to this. So b square, that means the square of this second term here. The square of this term here will give me sigma square t. Okay. If you are not familiar with indices, this is the rule for the indices. This is how I arrive at from sigma root t square, how the square of sigma root t, how I get sigma square t came from these two formula. So you're going to have a look. So then in detail, you can pause any point, you can pause the video to have a detailed look at this and match it with the figures here, so that you know exactly how I derive from step to step. So then here we have to come from this step to this step, I use equation 6 and 7. So since this is basic algebra and I shall not deal into the detail, so this one I'm just basically getting this e minus d1 square out of it. Using algebra I get it out, so root 2 pi, and the reason I want to get this out, right, is this is exactly my m prime d1. Okay, you compare with this thing here, m prime d1 is just x replaced by d1, I'll get e minus d1 square over 2, isn't it? and that's just this here. So I'll get it out so that I can change it to this. I'll get one step closer to the formula here. And E, this one, those after getting out the minus d1 square, I'm still left with the minus 2d1, minus minus become minus times minus become plus, and the 2 cancel away with the 2 here. The 2 cancel away with the 2 because divided by 2, so there's no more 2 here, so left with d1 sigma root t, d1 sigma root t, and minus, okay, this thing need to divide by 2, okay, and then minus multiply in, so you get minus here, so you get minus sigma square t over 2. That's how I arrive to this step. Then the third step, I make use using 4 and 2, that means using this equation, over here, I change this part to this part. This is using 4, and using 2, okay, this one I change the I didn't change anything else actually. In fact, I only changed this. So I'm going to, from here, I'm going to move on to the next page to continue with this formula. So you see that this part is exactly the same as the one in the previous page. We have m prime d1. You see we have m prime d1. We have k minus ert, ke minus rt, ke to power minus rt, and then we have this e d1 sigma root t minus sigma square t over 2, so which is the thing here. So it's exactly the same. I'm just copying over to the other page. So now we have m prime d1. I need to prove that I already have this over here. I just need to prove that the rest of this is the same as this one. So the trick is using 7, the equation 7 from the earlier. Okay, what is equation 7? Let's take a look. Equation 7 is this. Okay, so just basically just e, that means this e plus this is equals to e of this times the e of this, but e of this multiplied to e of this, that's why you get the rt minus rt over here is in this law or power rules. Okay, so then the k, I will just move over to his side because a multiplied to b is the same as b multiplied to a is the same, so k is multiple is commutative, so I bring the k over in front, and doesn't matter much. So e ln we just know that, okay, e ln x equals to x. This is log rules, right? So we just then the x we just bring down, so x in this case is like my s naught over k, so s naught over k, bring e ln would disappear, ln and e or e ln would disappear, so it's the same. Okay, so this is another rule, same rule for log rules. So they are the e and log are or log base e, we prefer to call it log base e. They are the inverse of each other. The exponential and the log base e are inverse of each other, so when they are together they cancel off and leave you back with the original x. And so here then we have this thing would become it will become this, so this would simplify to this part. Okay, this part will simplify to this part, and rt minus rt is 0, right? And then e to the power of 0 is just 1, and so k would cancel with k, so I'm left with s naught, so we result in s naught m prime d1. So that would be the I have proof for the 1a. That would be the second part of this video. So for the rest of the video, again, you can visit to see the other parts of the video. If you cannot find, just give me an email. .com. Okay, that's it. I'll proceed to the third part. To prove, I'll end the video here. I'll proceed to the third part in another video. Okay, so come to the third part of the 3-part video on call option pricing. Okay, this is the third part of the 3-part video, so you can find the other rest of the videos at www.hour.com. And this on call option. The first part I have explained what is a call option, and the second part I have explained how to prove this equals to this, and then in this third part of the video, I'm going to prove the rest of the equations related to the call option Schole call option pricing formula. So okay, for this thing, when we differentiate the d1 which is the d1 as stated here, when we differentiate the d1 respect to s0, it will be equals to, when we differentiate d2 with respect to s0. This is what we are going to trying to prove. And because we know that d1 is, again, the d1 is equals to right here we see d1 is equals to d2 plus sigma root t. So I just bring over basic algebra, I just bring over, so my d1 would be equals to d2 plus sigma root t. Okay, so then that's why when we come to here, I just change d1 to d2 plus sigma root t. And when we differentiate with respect to s0, all these other expression sigma and root and the t would be, we treat them as fixed. So when we differentiate with respect to s0, this thing just becomes 0. So ds0 sigma root t is just 0. But when we differentiate s0, then with d2 is a variable dependent on is a function of s0, so it should remain. So that's how I prove that differentiating d1 respect to s0 is same as differentiating d2 with respect to s0 will give you the same. So in the part 2b of the tutorial, okay, we are it means the tutorial given by the course on financial maths. Okay, so this Black-Scholes price formula, I was supposed to find dc not over ds0. Okay, so we are supposed to differentiate this with respect to s0. So we will differentiate implicitly. So that means differentiate this with respect to s0. That's what we get for here. And when we differentiate this term with respect to s0, this part, okay, this part we will differentiate using the chain rule. So the chain rule of the differentiation, so you can Google if you to find out what's the chain rule. So basically I'm differentiating this function m prime and keeping inside the input, keeping input inside, and then after that, while I differentiate the whatever is inside this bracket with respect to s0 as the chain rule. So actually because all this part and the d1 both contain s0 as a part of the variable, because you see the d1 contains the s0 as d1 is a function of s0, so it will not goes to 0 when you differentiate it. Instead, it will just remain as remain there, right? So then no, not this page, so here, so it will just remain here. So we'll keep this, differentiate this part, we'll get this is just the product rule, and then we'll keep the other nd1 product rule of differentiation. So we keep the nd1 and then we differentiate s0. When differentiate s0 with respect to s0, we just get 1, so we cancel it off and replace with 1 times nd1 still nd1. So after that, minus, okay, this part we treat it as just a constant, okay, because these are not functions of s0. Okay, so then when we differentiate this part, we use the chain rule again and we get this. Alright, and then using equation 11, okay, using equation 11, we know that differentiating d1 with respect to s0 is the same as differentiating d2 with respect to s0. So therefore I change this d2 from here to here. I keep everything from this equation to this equation over here. I keep basically everything except I change this ds0 d2 to ds0 d1. Okay, so because they are equal by equation 11, they are equal. So then the next thing that I do is I just factorize out. So because there's these two terms are the same, so I just factorize it out, and I keep this part, I just come to here and this part will just come to here. Basically this is basic factorization, and this nd1 I bring over to the other side, so to this part. So then because in equation 10 earlier, in the earlier tutorial, we have proved that s naught m prime d1 equals to ke minus rt n prime d2. This is the same as saying s naught m prime d1 minus ke minus rt m prime d2 equals to 0. Okay, and this thing you realize is just this, they are the same. So this part, since that is equals to this formula is equals to 0, right, and this is, so that's, this is equals to 0, so it changes 0 0 multiplied to anything is just 0, so I'm left with nd1. So this is how we show what we find this one. Okay, so the answer to this question is this nd1. All right, and come to the next part. We are asked to prove that the let's say if we differentiate the call price of the call option by sigma, the volatility the volatility of the share price. Okay, so and we differentiate this, we are asked to show that they are equal, and indeed we are able to show that using again just the chain rule, and we find that, yep. Okay, so keep this, for this part I'm keeping s naught, okay, and differentiate this m prime d1 with respect to sigma. Now s naught is just when differentiating respect to the volatility sigma, s naught is not a function of sigma, so you just treat it as a constant, so like fixed. So then m prime, when differentiate this thing, we just use the chain rule. Okay, the differentiate this function, and then keep the inside, and then differentiate the inside, which is the chain rule. So then after that, minus ke minus rt, I'll keep it because this is not all these terms are not the function of, they are not functions of the sigma, so you just treat it as a constant. And then again, when I differentiate this with respect to sigma, and differentiate, this is this function, and so this is still the chain rule. Okay, then we will stop for this one here. We'll not simplify the expression further because it's not necessary, and let's differentiate the price of the put option with respect to sigma. So the put option price sync model is this. Okay, you can Google for the put option Black-Scholes put option pricing model, and then you get this formula, and just need to differentiate this and then get the using chain rule as well, and chain rule as well. So same thing as earlier. So then we know that the probability distribution function for the normal distribution is just this formula, and then when we replace minus x with minus x, we still give us the same thing, because the square minus x square is just x square, and then there's a minus in front. So then that means this and this are, the two are equal. So that means the m prime d1, if I replace inside with d1, and this minus d1 will also be equal. So if they are equal, then that means that when I follow from here, let's say this, I just minus d2 would be the same as n prime minus d2 would be the same as m prime d2. That these two would be the same, they are because of this formula. So then here we have ke minus, so differentiate this thing, we are just skipping everything else. So then this minus d1 I change to d1, okay, also because of this formula here. So then the rest I'll keep it the same. Then differentiation, and we know that when you differentiate, when there's a negative sign in front of the function that we are differentiating, we can actually bring the negative sign to out of it. So seems, therefore I'm trying to bring in the next step, I bring the minus here to the front, and the minus disappear from here, and here the minus here I also bring to the front, and minus multiplied to a
negative, so it becomes a plus over here, and the minus here disappear. So and therefore we arrive at this for the d over d sigma p naught, and we realize this is just exactly the same. Comparing this the equation 13 and equation 12, we realize compare the right hand side, we realize the expressions, this expression is exactly the same as this expression, which means that this is the same as this, right? So then we are done with this 3-part tutorial. You can find the other two parts of the tutorial at www.owl.com under maths video links, and under financial mathematics. Okay, um okay, thank you, then that's all for this tutorial.